Think about OSPF and EIGRP for a moment. Now, I know we're here to talk about BGP, but let's pause and think about those IGPs for a moment. How do they determine the best path? How do they know what gets installed in the routing table? Well, in EIGRP's case, they use the feasible distance calculation, those K values. And in OSPF's case, they basically use a aggregated accumulation of bandwidth. Wouldn't it be nice if BGP just used one single metric to determine what the best path is? It would be nice, but that's not the case. BGP uses a series of factors or metrics or other items to determine what the best path it should select is. I mean, think about it. It's the protocol of the internet. A service provider's router is going to be learning a route from possibly dozens or even hundreds of different routers. It's going to see a bunch of different advertisements and a bunch of different paths, so how it determines the best path is going to be kind of complicated. This skill is going to be all about what are the actual steps that router will take to determine what the best path for a certain prefix is going to be. Some of those determining factors are kind of involved. There's going to be a little bit of demo. Others are very straightforward. So get ready to see it in the whiteboard as well as the virtual lab. Let's get going. It's going to be big and fun. Up until this point, we haven't talked much about BGP's best path algorithm. What are the processes that it goes through when determining what is the best path? We have demoed a little bit of it though. If you followed along in the nugget on route maps, you saw where we set the weight on a path coming in order to manipulate how that traffic actually worked. And that's what we're going to talk about in this nugget, is actually about weight. But before we jump into weight, let me set up the scenario about how BGP is doing what it's really doing. Think about this scenario for a second. We are a service provider. We have a bunch of clients. We've got a router here. What happens when we start peering with other service providers? Maybe we've got a service provider here. We'll call this service provider A, service provider B. Over here, we'll say we've got service provider C. And all of these service providers start advertising routes into us. Then we take it a step further and we start advertising those routes through IBGP, or maybe we advertise it outbound through eBGP. You could even look at it as a route comes in from service provider A, we're going to advertise it back out to B, C, and so on. How does BGP then determine if this route came in from all of these different service providers? How does it know which one is best? Well, at the fundamental level, BGP just has a list of attributes that it goes down one at a time. So for now, we'll just call this attribute A, attribute B, attribute C. So when service provider A advertises a NLRI to us, it not only has that prefix, but it also has the attributes. Recall, that's what makes it an NLRI, the Network Layer Reachability Index. Service provider B advertises in an NLRI for the same prefix, but it may have different attributes. And BGP is going to go down the list comparing one attribute at a time. And when it finds a difference in those attributes, that's when it determines which attribute is best. So what this skill is really talking about is which attributes does it look at, and then how does it determine if one of those attributes is better than the other? So let's clear the screen and start by talking about our first attribute in the BGP selection process, and that's weight. Weight is a big one. Weight is an important one. So here we have our router once more. We'll put service provider A back on the map, advertising a route in. Service provider B back on the map, advertising a route in. Here's where weight comes into play. Weight can only be set directly on the router that it comes in on. We do not advertise weight to any other routers. So if I'm advertising out through eBGP over to a different service provider here, or if I'm advertising to an IBGP within my autonomous system, weight will never be sent with my NLRI advertisements that are going outbound. Where weight comes into play is if we want R1 to explicitly determine that the advertisement that came in is the best, and that's where we should always prefer traffic. For instance, service provider A sends in a prefix, make something up, for 100.0.0.0/8. Service provider B sends in a prefix 100.0.0.0/8. And everything about these advertisements otherwise will be identical. For whatever reason, let's say we've created a policy that says for traffic destined to 100.0.0/8, always use service provider B. When service provider B's advertisement comes in, we'll create a route map that sets the weight on this router for that prefix. The higher the weight, the more preference it gains. And by default, prefixes that come in have a weight of 0. So all we have to do is set it to any number greater than 0, and by default, that prefix will win. The best example of this was in our virtual lab. Let's draw up a perfect scenario as to why we would implement weight. In our virtual lab, we had R2 and R3 as part of AS100. So if I'll draw a little dotted line here, we'll say this is AS100. Then at the top of this topology, we had R4. When R2 and R3 advertised routes upwards towards R4, it had to choose which path it liked best. And later down the line, we'll talk about how it got to this point, but R4 was choosing R2 as the best path, when it actually wasn't. You see, this link was using fast Ethernet, whereas this link over here was using gigabit Ethernet. So a perfect reason why we may want to implement a weight would be right here on R4, setting the weight of routes coming in from R3 to 100. Or really any digit that's greater than 0. That way R4 will put a preference of traffic going outbound towards R3 when it's destined for AS100. Let's fire up the virtual lab and get this in action. With the virtual lab fired up here, I'm going to jump over to R4 and quickly give it a show BGP IPv4 unicast just to get a lay of the land, and you can see exactly what we were talking about here. We've learned all of these 1.1.1 routes, and we're preferring the routes towards R2 right now, but this is using a less than optimal path, because if I give it a show IP interface brief, we can see our link towards R2 is using fast Ethernet, whereas our link towards R3 is using gigabit Ethernet. So let's fix this with a route map. I'll start by creating a prefix list that grabs all of those 1.1.1 routes. I'll call the prefix list filter 1. I'll say permit 1.1.1.0/24, so it grabs any 1.1.1 address. And I'll say greater than or equal to 32 because it's going to be a 32-bit mask. Now I'm going to create a route map that's going to be for our neighbor relationship with R3. So I'll call this R3 wait. I'll specify a permit statement, sequence number 10. Then I'll match on the prefix list. So I'll say match IP address, prefix list, filter 1. Nope, got to spell filter right. There we go. Now I'm going to set a path attribute as it's coming inbound. If I hit question mark here right after set, there's actually a lot of things that we're about to talk about coming up. Here's wait, but we can also see things like metric, local preference, community, AS path, origin. Quite honestly, almost all of the things that are used in the BGP best path algorithm can be manipulated in a route map. For now, let's stick to wait. I'll specify wait, set the wait to 100. Now for my route map, I want to just have a permit statement that grabs everything else. So that way we're not accidentally filtering out any routes with an implicit deny at the end of the route map. This route map was called R3 wait. I'll specify permit, sequence number 20, press enter, and now I can exit out of route map configuration mode. I'll jump into BGP configuration mode, and I'll adjust my neighbor relationship with R3, 100.100.34.3, and specify let's use a route map of R3 wait for routes coming inbound. We do have to specify the direction there. I can press end. We can quickly make our policies and routes refresh by doing a soft reset. So I'll say clear BGP IPv4 unicast, specify the router's IP address. Then the direction will be inbound. I'll press enter. Now lastly, I'll give it a show IPv4 unicast and we'll check out the routes. Now I see all of my 1.1.1 addresses are preferring router 3 because they have a wait set to 100. So when all else fails, you can set a wait on routes coming inbound to tell that local router prefer the route coming from this specific provider or partner or neighbor over any of the other advertisements. So that's the first criteria that goes into the BGP best path algorithm wait. In the next nugget, we're going to talk about local preference. In the meantime, I hope this has been informative for you, and I'd like to thank you for viewing. So wait was great and all for making a last minute judgment. This router should prefer traffic towards that destination. But what happens when we start disseminating that route through our own autonomous system using iBGP? Remember, wait stayed on that router. So if we were having to manipulate each path with a route map that set the wait, we would have to set that on every single router. It may be preferable and more efficient to be able to set a metric that BGP prefers throughout an autonomous system. Let me draw it up for you. Let's think one more time about this scenario where we've got our R2 connection here and our R3 connection here, both of these go up to R4. The R2 connection is still using fast Ethernet. The R3 connection is still using gigabit Ethernet. And there are a couple other routers in this topology within our autonomous system, R1 and R11. It looks something like that. What happens when R4 wants to advertise its loopback 4.4.4.4 down to each one of these devices? Ultimately, Autonomous System 100 wants traffic destined to 4.4.4 to go out through R3. So what R3 can do is set something called the local preference. This is what comes up second in the BGP best path determination. If none of these routers are setting a weight, all of them will have a 0. So it needs to go to the next criteria to compare to determine what's best. And in this case, local preference can be set by a router, and that will be sent to all of the other BGP neighbors. Now, local preference does get a little bit quirky. For instance, when R4 advertises 4444 down to R2 and R3, by default, R2 and R3 set a local preference equal to 100, then advertises that to all of its iBGP neighbors. So if we want a path to be preferred within the topology, say through R3, we would need to tell R3 to advertise a local preference greater than 100, maybe something like 200. What's particularly interesting is when R3 advertises the NLRI with a local preference of 200, R2 will then withdraw its advertisements for that prefix. Again, all of this is accomplished with a route map. So let's fire up the virtual lab, build a route map that sets the local preference, and then watch how AS100 handles it. So with the virtual lab launched here, I'm going to do a show IP interface brief on R4, and we see we've got a loopback of 4444. It's not being advertised in BGP just yet. So I'm going to say router. Nope, I'm not going to say router from privilege mode. We're going to jump into configuration mode, and then we're going to say router BGP 200. Let's advertise that loopback 4.4.4.4, mask 255, 255, 255.255. Press enter, end, and back out. Now we'll jump over to R1 in AS100. Let's just give it a show IPv4 unicast. Take a look at the BGP table. Okay, I see I've got 444 here advertised from 100.100.24.4. The local preference is 100. In fact, all of these are 100, and all of these were advertised by R2. From R2's perspective, I'll say show BGP IPv4 unicast, and we see the 4444 address was advertised from R3 as well as the eBGP relationship over on R4. Now, at this point, you may be curious, going like, wait a minute, local preference here is 100, and there is no local preference for the route that was advertised by eBGP. Why then did it choose the route advertised from eBGP? I mean, the selection criteria was weight, and the weight here is 0 for both of these. So then it goes to local preference, right? And here we have a local preference of 100 and then a local preference that's null. Well, at the time that BGP is evaluating this criteria, when it gets to local preference and it finds one that's empty because it was an eBGP learned route, it default sets that to 100. So at the time of evaluating local preference, these are actually equal, and it goes down the road and uses a different piece of criteria to determine why this route was better than this one. Let's manipulate this, though, so that R3 advertises a higher local preference, and then R2 would prefer to send traffic over to R3 and then up the gigabit Ethernet link. From R3, we're going to go into configure terminal. We're going to set a prefix list here. I'll call this for route. We'll say permit, and then the 4.4.4.4/32 prefix. Now I'll go into route map. I'll call this my R4 route. This will be, again, permit and sequence number 10. I'll match on IP address prefix list. That was called for route. And we're going to set the local preference equal to 200. Jumping back into route map real quick, I'll make sure to give it another permit statement. That way it catches everything else instead of an implicit deny. Oop, not end. Then I'll go into BGP 100 configuration mode, and I'll set my neighbor of R4 to have a route map of R4 route coming inbound. Oh, too many characters there. There we go. End. I'll just give it a soft inbound reset. We'll say inbound. That way it resets that connection to R4, processes those inbound policies one more time, and now when I jump over to R2, if I give it a show BGP IPv4 unicast, look at this. Now R2 prefers the route towards R3 because it has a local preference of 200. Beyond that, if I jump back over to R1, hit the up key there, run it one more time, look at this. Right here. The advertised 4444 address now is being sent to R3. That's because R2 is serving as a route reflector and R1 is the route reflector client. So when R3 advertises a preferred route, R2 installs that into its table, sends its withdrawal request to all of the neighbors that it advertised to, and then reflects the preferred route to the route reflector clients. So that's been how we can use local preference to set a preferred route within an entire iBGP autonomous system. I hope this has been informative for you, and I'd like to thank you for viewing. The next two BGP best path selection criteria that we need to talk about are the originator and the AIGP, Accumulated Interior Gateway Protocol. Now, there's not much to the originator. Basically, a router is going to look at a prefix or an NLRI that's coming inbound, and if it originated that prefix or NLRI, it's going to choose what it originated. Otherwise, it's going to pick the NLRI that's being advertised to it based on some other criteria. In fact, let's jump on the whiteboard real quick. In a scenario where R1 advertises its loopback through iBGP to R2, who then advertises it down to R3, who then advertises it back to R1, R1's going to be able to look at this advertisement that's coming in and say, wait a minute, I originated this with my network statement. And it knows to pick its own NLRI, the one that has a next hop of 0.0.0.0. The third command of BGP's best path algorithm looks at the following characteristics. For the NLRI, it's looking at who the originator was. So if I put a little A here, if R1 originated this loopback address with either the network statement or redistribution, this is the criteria that would win. If R1 originated this with the aggregate address command, this is the next criteria that would win. And then lastly, if R1 didn't originate it and it was learned on an inbound NLRI, that is the next criteria. That really is all there is to say about the originator and the third selection criteria. So first there's weight. Then there's local preference. Then we're looking at if we originated these with a network statement, a redistribute statement, or an aggregate address statement, or if this was an inbound NLRI. So with that one under our belt, let's move on to the fourth criteria, and that's AIGP. It's been suggested numerous times that BGP actually use the underlying IGP's metric in order to determine the best path. But this isn't feasible because when carrier A peers with carrier B, what happens if carrier A is running OSPF and carrier B is running EIGRP? We don't have control over our peers' interior gateway protocols, and therefore the metric just falls apart when it moves from one peer to another. However, if we are a service provider and we have multiple autonomous systems here, we can control the IGP that is running in each one of these autonomous systems. So for instance, if all of these are running OSPF, we can configure BGP as it's moving from one of our autonomous systems to the next autonomous systems to factor in the IGP's metric and pass that metric along from one device to the next. This is using something called, well, I'm just going to write it here, AIGP, Accumulated Interior Gateway Protocol. Each router has to agree that they are going to run AIGP the whole way through the path. That way the metric can be accumulated as it moves from one autonomous system to the next. Configuring AIGP is very easy. It's one command. Now, I would love to jump in the virtual lab and show you how to configure AIGP, say from R3 up to R4, except that the commands to enable AIGP are actually relatively new. And older versions of iOS simply don't support AIGP or this new command. But perhaps in an exam environment, you may encounter one of the newer versions of iOS and you need to know about this command. All it takes to enable AIGP and start passing IGP metrics back and forth is the neighbor statement, our neighbor's IP address. I'm just going to put this in a little caret here. Then AIGP. BGP. That's it. So for instance, we ran that command on R3 with regards to R4. Then we jump over to R4 with regards to R3. And these two would detect that our peer's capabilities include AIGP. So if I jump over to the virtual lab really quick, clear the screen, and I give it a show BGP IPv4 unicast neighbor, I'll call out my specific neighbor of R4. That's 34.4, sorry about that. Right here, under the 4 address family IPv4 unicast, you would be able to see one of the capabilities listed right in this section, that it is AIGP enabled. So as routes get advertised all the way down to R3, or maybe all the way up to R5, it would be accumulating a metric, and that would be the 4th criteria that it determines as the best path forward. So that's been the originator and AIGP. I hope this has been informative for you, and I'd like to thank you for viewing. Now, a lot of people would argue that this next item, this next bullet point, this next selection criteria that we're about to cover, autonomous system path, is the most important selection criteria in the BGP algorithm. The reason why is that if we don't change anything like the weight, the local preference, or AIGP, this is the criteria that will most of the time be used to select the next stop. While our lab environment is relatively simple, think about the size of the internet for just a moment. How many advertisements for one prefix are we going to receive from all of our peers? We're going to receive that advertisement so many times from multiple carriers, and all of them are going to have varying AS path hop counts. So this is the selection criteria that most commonly is used to determine the best path. Let's jump on a whiteboard and see how it looks in action. Let's pretend for just a moment that each one of these routers also represents the number of their autonomous system. So R1 here represents AS1, R2 here represents AS2, and so on. When we receive prefixes from R8, R3, and R2 regarding a route to R5, this is when the selection algorithm is going to make a determination. You see, if it were to follow this path here, it would hop to autonomous system 7, 4, 8, and then 1. So our AS path here is going to look like 7, 4, 8. And then it would end up on 5, followed by an I, meaning that the network was originated with a network statement within autonomous system 5. The path going from the top would look like 5, 6, 2, and then the I here. Whereas the path here would look like 5 and 3, an I. So the AS path would determine that this path right here is the best one because it only has to traverse the 2 autonomous systems, 3 and then 5. Up here, it would have to traverse autonomous system 2, 6, and 5. And down here, it would have to go through 8, 4, 7, and 5. So as long as we're not setting something like weight or local preference, or maybe using an AIGP somewhere, this rule, rule number 5, the AS path, is what's going to fire off and make a selection that the next hop address of R3 is going to be what's installed in the routing table. So while that seems pretty basic, it is worth pointing out that you can use a route map to add autonomous system hops to the AS path. So we can absolutely manipulate an advertisement outbound to include more hops than would be necessary as part of our path attributes in an NLRI. It's just something that you should know about, that as per usual, you can use a route map to manipulate just about any part of a path attribute, including the AS hops. So that's been rule number 5, the AS path. I hope this has been informative for you, and I'd like to thank you for viewing. In this nugget, we're going to talk about the 6th and the 7th factors in the BGP best path algorithm selection process. First up, we're going to be talking about the origin type. Now, when we talk about origin type with relation to Cisco routers, we're trying to figure out, did this come from a network statement or was this redistributed from an IGP into BGP? Jumping on the whiteboard, let me tell you how this really breaks down. Now, technically, there are 3 different origin types, and they're preferred in this manner. The first is I, meaning this was originated internally from an IGP using the network statement. Anytime that you looked at those AS paths and you saw something like 500, 400, I, that's what we're talking about here is the I. Less commonly used, in fact, almost impossible to find on a Cisco router, is E for an externally learned ENLRI. And the reason why you never see this is because pretty much every route starts somewhere with a network statement or redistribution. So you should know that E exists, but really the selection criteria comes down to I or question mark. Question mark technically means incomplete, meaning we don't know the entire path of this NLRI because redistribution occurred somewhere along the way to pull this route in from a different IGP. Let's jump into the virtual lab and see this in action. I'm on R3 right now, and if I give it a show IP route, you can see what kind of routes we have here. Well, immediately, what should draw your attention is these OSPF learned routes. Now, you would never want to redistribute your internal routes into BGP. This is just for a lab demonstration, but let's do that. Let's redistribute these OSPF learned routes into BGP and then see how our peers receive these routes. So to get a lay of the land, I'll give it a show BGP IPv4 unicast. We'll make sure they're not there currently. They're not. And all of the routes that I have are showing the I. So we know that these routes are what's going to be preferred. Now, route redistribution from an IGP into BGP is not as risky as doing it in the reverse. BGP can have hundreds of thousands of routes. If we were to redistribute from BGP into IGP, that could create major problems. But from BGP configuration mode, I can simply say redistribute OSPF process 1, and if I give it a question mark, we can even set a metric, which is what our next topic is going to be all about. So let me do that. I'm also just going to throw in a metric of 30 just to make something up, and we'll talk about what role that metric played in just a moment. Now BGP has redistributed OSPF into BGP, so if I exit out of configuration mode, go back to show IPv4 unicast, BGP IPv4 unicast, now we see our incomplete paths, don't we? And this means that these routes are also being advertised outbound towards our neighbors. So let's jump over to R4, give it a show BGP IPv4 unicast. And I can quickly identify the differences between the internally originated NLRIs that came from a network statement versus ones that were originated from redistribution. If there were to be a tiebreaker scenario, the I's would win over the question marks. But now it's time to talk about the metric. Metric, in this case, is often referred to as the multi-exit discriminator, or MED, but that's what shows up in the metric column when we advertise routes outbound. There are a lot of rules and best practices that go into the metric. Here's the summary of them. When R3 redistributed routes into BGP, it also set the metric of 30 on those routes. So it advertised a prefix to R2 with a metric of 30. And it advertised that same NLRI up to R4 with a metric of 30 as well. This 30 metric is not what we call transitive. That means R2 isn't going to forward the prefix with the metric involved with it. So R2 did forward the NLRIs, but it omitted the 30 metric when in that advertisement. So R4 in its BGP table learned about the 172.16 prefixes from R3 and R2. R3 originated it with redistribution. The difference now between these is that R2 will not have a metric and R3 will have a metric of 30. The rule of thumb in this case is to prefer routes that do not have a metric. That is the default rule. But if both routes were to have a metric, maybe this one had a metric of 90, then the rule is then to prefer the one with the lowest metric. You can kind of think of it like feasible distance or OSPF's bandwidth cost. You'd want the lowest one first. So let's jump over to R4 and look at the BGP table and verify that this is the behavior that occurred. Back on R4, I'll give it a show BGP IPv4 unicast. Hit spacebar a few times, and I can see the redistributed routes because they have the question marks here. And look at this. The R3 learned routes do indeed have a metric of 30 set on them here. But the ones that were preferred and installed in the routing table were the ones that were R2 because it didn't contain a metric. So my quiz question to you at this point is what were to happen if we went to R2 and then advertised these 172 networks with a network statement? Who would win? Then what would happen if on R2 we were to redistribute these 172 network statements into BGP with a metric of 90. Who would win then? I'd encourage you to stay in the virtual lab and work through both of those scenarios so that you really understand the behavior of the origin type and the multi-exit discriminator. In the meantime, that's been rules number 6 and 7. I hope that's been informative for you, and I'd like to thank you for viewing. Now, the next item is a relatively simple one, but it's a big one that you need to understand and you need to see it in action. We're talking about eBGP learned routes versus iBGP learned routes. Let's jump in the virtual lab and see it in action. To refresh your memory one more time, we have R2 and R3 who each have eBGP connections up to R4. They then have an iBGP connection to each other. So when R4 advertises its loopback address 4.4.4.4, it'll advertise it down to R3 as well as to R2. But then R3 is going to advertise this over to R2 as well, and vice versa. So R2 will learn about 4.4.4.4 from R3, an iBGP relationship, as well as from R4, the eBGP relationship. And the selection algorithm here says eBGP always wins over iBGP. We can verify this by jumping in the virtual lab and taking a look with our favorite show command. Once we're on the virtual lab and we've jumped over to R4 and we've issued the network statement to advertise that local loopback address, we can say show run section BGP, verify that we've got it advertised. Yep, it's right there, network 4444. So I know it's being advertised. I can jump back to R2 and give it my favorite command, show BGP IPv4 unicast, and there it is right there. Now, I know your eyes may have gone towards these eyes before, but that's not the eye we're looking for this time. Now we're looking for the eye that's right here. We can see that this route for 4444 has the little caret indicating that it's the best path right there, but we don't have the little eye here indicating that it was learned internally. You see, this route was learned from R3, our iBGP neighbor, and this route was learned externally from R4, our eBGP neighbor. And because eBGP always wins over iBGP, that's the one that was selected in this case. Now again, I called it out earlier that the local preference being blank, that's what really threw me for a loop the first time I was learning BGP. Under the hood, there is an implicit 100 calculated here. So as it went through all of the other selection criteria, for instance, the AS path is the same. The origins both end with I. The metrics here are 0. So then it falls to eBGP over iBGP. And that's how the route to 4444 was selected. We can jump over to R3 and verify a similar result. Sure enough, our externally learned route was selected over our internally learned route that we received from R2. So that's been eBGP over iBGP as rule number 8 in the BGP best path algorithm. I hope this has been informative for you, and I'd like to thank you for viewing. Now at this point, there are 5 attributes remaining that BGP uses in its best path selection algorithm. Here's the thing though, they're really just tiebreakers at this point. They don't need a huge amount of explanation because they simply exist when all else fails. Let's jump on a whiteboard and draw up what those remaining 5 attributes are. The next and the 9th attribute that we're going to be reviewing here is the lowest IGP metric. In this case, we're pretending that R1 here maybe is advertising its loopback address or something like that of 1.1.1.1 down into this blue autonomous system. If we're looking from the perspective of R4 or R5, it's going to learn about this path to R1 through 2 different channels. An advertisement is going to come down this way and then over to R4. And then an advertisement is going to come down this way and then over to R5. And then they're going to exchange paths back and forth. So if R4 wants to get to R1, all of the other metrics up to this point from its perspective are going to be identical. If we don't set a weight or a local preference, if we're not using an AIGP, the AS path count is going to be the same. These are learning about these from internal BGP. It's going to fall down to what is the lowest IGP metric. In this case, it will probably have a lower cost going this path to R2, and R5 will probably have a lower cost going this path to R3. Now, unless there's a fast Ethernet link somewhere along the way that could throw everything off, but if we're assuming that all of these links are gigabit Ethernet or 10 gig Ethernet, then from R4's perspective, this path would be best, and R5's perspective, this path would be best. Going this path from R5 may be too long, and this path from R4 would be too long as well. So that's the 9th metric, the lowest IGP metric. The 10th metric is going to be the oldest eBGP learned route. The reason that this exists is because routes are coming and going all the time. Routes are flapping all the time. The oldest eBGP learned routes are probably indicative of the most stable routes. So that's why it picks the oldest eBGP learned route rather than one that may be coming in and then going out and then coming in and then going out and so on. The 11th tiebreaker here is the lowest neighboring router ID. Recall that the router ID by default is the highest addressed loopback, and if there are no loopbacks, it's the highest addressed physical interface. If I fire up the virtual lab for just a moment, from R2's perspective, I can say show BGP IPv4 unicast neighbor, because I want to look at details of my neighbor, like what is R1's router ID. I'll specify my neighbor relationship here, going towards R1, and we can see that R1's router ID is 1.1.1.4. the highest address loopback. It's in fact a best practice to manually set your router ID so that in the event that you introduce new loopbacks, it doesn't create these flapping sessions or flapping routes, because now we see that our router ID can actually be used in the selection process. So by simply creating a new router ID, we could be throwing off some downstream selection process that's happening. Very quickly, we can go into configuration mode, router BGP 100, and then we can specify our router ID with BGP router ID, and then specify something like 2.2.2.3 or 4, because I accidentally typed 4. But you notice what happened the moment we changed the router ID? All of our connections went through a hard reset. So keep that in mind, that if you've built a neighbor adjacency already and then you go to change your router ID, it will tear down that adjacency and then rebuild it. The 12th factor that's used in the BGP selection algorithm is the minimum cluster list length. The cluster list is an attribute that's set on a route reflector as it's reflecting a route. So as routes get reflected around an iBGP autonomous system, if a route takes too many bounces, BGP can look at all of the route reflectors that it's passed through and choose the most efficient route by choosing the minimum cluster list attribute that was set. And lastly, the very last selection item that's used in the BGP selection process is the lowest neighboring address. So if all else fails and everything else is held equal, BGP can look at the lowest IP address of our neighbors, and that's the path that it will choose to go towards. So that is the BGP best path selection algorithm steps from 1 to 13. I hope this has been informative for you, and I'd like to thank you for viewing. So it's been a whirlwind of a ride as we've talked about all of the different path attributes that really make up the BGP best path selection algorithm. I'd like to really emphasize the point that we can use route maps for just about any of these path attributes to manipulate what we believe is the best path or the selected path that should be used to move forward. As always, jump back into these videos and walk through those virtual labs and just experiment with all the ways that you can manipulate the BGP best path selection algorithm. So that's been the BGP best path selection algorithm. I hope this has been informative for you, and I'd like to thank you for viewing.